Day 6. Description of composite structures. Introduction. Composite materials are becoming more important in the construction of aerospace structures. They provide an increase in strength with a reduction in weight. Newer generation of large aircraft are designed with all composite fuselage and wing structures, and the repair of these advanced composite materials require an in-depth knowledge of composite structures, materials, and tooling. Laminated structures. Composite structures consist of a combination of materials that are mixed together to achieve specific structural properties. An advanced composite material made of a fibrous material embedded in a resin matrix, generally laminated with fibers oriented in alternation directions to give the material strength and stiffness. Laminated structures. Applications of composites, fairings, flight control surface, landing gear doors, leading and trailing edge panels on the wing and stabilizer, interior components, floor beams and floor boards, vertical and horizontal stabilizer primary structure on large aircraft, primary wing and fuselage structure on new generation large aircraft, turbine engine fan blades, propellers. Major components of a laminate. Isotropic, a material that has uniform properties in all directions, example aluminum, titanium, and multiple layer composites. Anisotropic, a material that has different properties or strengths when measured in different directions, example unidirectional composite tapes. A composite part may be designed so that the fiber arrangement produces the strongest part, but they can only approach the true isotropic nature of metals, such as aluminum and titanium. A matrix supports the fibers and bonds them together in the composite material. The matrix transfers any applied loads to the fibers. Strength characteristics. Structural properties such as stiffness, dimensional stability, and strength of a composite laminate depend on the stacking sequence of the plies. Drop test. Conventional carbon fiber filament wound hollow care. Baseline chromally mild steel. OEM steel main structure. Aluminum. Baselines. OEM steel reinforcing, carbon fiber Kevlar composite. Fiber orientation. The strength and stiffness of a composite buildup depends on the orientation sequence of the plies. Proper selection of ply orientation in advanced composited materials is necessary to provide a structurally efficient design. It is critical during a repair to replace each damaged ply with a ply of the same material and ply orientation. Fiber forms. Filament, individual fiber. A bundle of filaments are identified as tows, yarns, or rovings. A roving is a single grouping of filaments or fiber ends, such as 20-end or 60-end glass rovings. All filaments are in the same direction and they are not twisted. Carbon fiber rovings are usually identified as 3K, 6K, or 12K, K meaning 1,000 filaments. Types of fiber. Unidirectional tape, a standard within the aerospace industry. Typically impregnated with thermosetting resin, tape products have high strength in the fiber direction and virtually no strength across the fibers. The fibers are held in place by the resin. Tapes have a higher strength than woven fabrics. Spread toe fabrics. Spread toe fabrics use tapes instead of yarn. In any given area, more fibers can be packed in tape form than in a yarn. A woven material comprising interlacing fibrous tapes instead of yarns displays a substantially reduced number of interstices/openings. This means that a tape-woven structure presents less accumulation of matrix at the interstices and hence increased fiber volume fraction. The spread toe structure makes it possible to achieve thinner laminates. Straighter fibers with reduced crimp optimize and strengthen the composite. Fewer crimps reduce the amount of excess plastic, thereby minimizing weight. Types of fiber. Bidirectional fabric. Woven structural fabrics are usually constructed with reinforcement toes, strands, or yarns interlocking upon themselves, with over-under placement during the weaving process. The more common fabric styles are plain or satin weaves. The plain weave construction results from each fiber alternating over and then under each intersecting strand. Types of fibers: nonwoven, knitted, or stitched. They offer many of the mechanical advantages of unidirectional tapes. Fiber placement can be straight or unidirectional without the over-under turns of woven fabrics. The fiber are held in place by stitching with fine yarns or threads after pre-selected orientations of one or more layers of fibrils. Types of fiber: fiberglass, used for secondary structures, fairings, raydowns, wingtips, also helicopter blades. Electrical glass or e-glass is identified as such for electrical application. It has high resistance to current flow. E-glass is made from borosilicate glass. S-glass and S2 glass identify structural fiberglass that have a higher strength than E-glass. S-glass is produced from magnesia aluminosilicate. C-glass used for chemical applications. Types of fiber: Kevlar. Kevlar is DuPont's name for aramid fibers. Aramid fibers are light in weight, strong and tough. Kevlar 29 has a low stiffness and Kevlar 49 has high stiffness. The main advantage of Kevlar is its high impact resistance, hence it being used in areas that are prone to impact damage. The main disadvantage or aramid fibers is their general weakness in compression and hydroscopy. Kevlar will also absorb up to 8% of their own weight in water. Kevlar is also difficult to drill and cut, so special scissors should be used. Bundles of Kevlar are not sized by the number of fibers like carbon, but by their weight. Types of fiber: carbon graphite fiber. Carbon and graphite fibers are based on graphene. Hexagonal layers networks present in carbon. If the graphene layers are stacked with three-dimensional order, the material is defined as graphite. If the layers are stacked in two-dimensional order, it is defined as carbon. Carbon fibers are stiff and strong, 3 to 10 times stiffer than glass fibers, used for structural aircraft applications such as floor beams, stabilizers, flight controls, primary fuselage and wing structure. Advantages: high strength, corrosion resistance. Disadvantages: lower conductivity than aluminum, high cost, potential for galvanic corrosion. Carbon fiber nanotube. Carbon types of fiber: boron, a very stiff fiber that has high tensile and compressive strength. Fibers are relatively large and do not flex well. Only available as a pre-tape product. Can be used to repair cracked aluminum aircraft skin due to its coefficient of thermal expansion being close to aluminum, and there is also no galvanic corrosion. can be hazardous for personnel primarily used in military applications. Very expensive to manufacture. Boron nanotube tech. Safety. Types of fiber: ceramic fibers, used for high-temperature applications such as turbine blades in a gas turbine engine. Uses a metal matrix with ceramic for a metal hybrid. The ceramic fibers can be used to temperatures up to 2,200 degrees. Ceramic fiber 3D printing. Lightning protection fibers. The surface of an external composite component often consists of a ply or layer of conductive material for lightning strike protection because of composite materials being less conductive than aluminum. Some types of conductive materials used for composites are nickel-coated graphite cloth, metal meshes, aluminized fiberglass, conductive paints. AA and P should always be aware when performing repairs that he or she should recreate the electrical conductive design. Should also be checked with an ohm meter to verify minimum electrical resistance across the structure. Matrix material. The term resin is a generic term used to designate the polymer. Thermosetting resins are the most diverse and widely used of all man-made materials. They are easily poured or formed into any shape, compatible with most other materials, and cure readily by heat or catalyst into an insoluble solid. Once cured, it cannot be heated and reshaped. Polyester resins. Polyester resins are relatively inexpensive, fast-processing resin used generally for low-cost applications, not used in structural applications, used more for mold-making tooling. Uses a peroxide catalyst. Vinyl ester resin. The appearance, handling properties, and curing characteristics of vinyl ester resin are the same as those of conventional polyester resins. The main advantage of vinyl ester resin is its corrosion resistance and mechanical properties. Used as a good intermediate between epoxy resin and polyester resin. Used a lot in the home-built market. Epoxy resin. Polymerizable thermosetting resins, available in a liquid or solid form. There are many different types of epoxy resins. The technician should always consult the maintenance manual to select the proper type for a specific repair. Advantages: high strength and modulus, low level of volatiles, excellent adhesion, low shrinkage, good chemical resistance, ease of processing. Disadvantages: brittleness, reduction of properties in the presence of moisture, semi-crystalline thermoplastic, used in secondary and primary aircraft structure. Available in multiple forms, ranging from injection molding to woven pregs. Advantages: flame resistance, superior toughness, good mechanical properties at elevated temperatures, low moisture absorption. Amorphous thermoplastics, available in several physical forms, including filaments, film, unidirectional tapes when combined with fibers, woven prepregs when combined with fibers. Some of the fibers used are carbon, aramid, and glass. The advantages of this resin depend upon the polymer, but typically they are noted for processing ease and speed, high temperature capability, good mechanical properties, excellent toughness and impact strength, chemical stability. The stability results in unlimited shelf life, eliminating the cold storage requirements of thermoset prepregs. fiberglass, prepreg glass, polyether, ether, pecone, PEEK. PEEK is a high-temperature thermoplastic that offers outstanding thermal and combustion characteristics and resistance to a wide range of solvents and proprietary fluids. It can be reinforced with glass and carbon. Thermoplastic resonance. Thermoplastics materials can be softened repeatedly by an increase of temperature and hardened by a decrease in temperature. Advantage: processing speed. Curing stages of resin. There are curing stages in resin which are called A, B, and C. A stage, components of the resin have been mixed, but the chemical reaction has not started. The resin is in the A stage during a wet layup procedure. B stage. The chemical reaction has started. The material has thickened and is tacky. Prepregs are in the B stage. To prevent further curing, the resin is placed in a freezer at 0 degrees F. C stage. The resin is fully cured. Some resin cures at room temperature and others need an elevated temperature cure cycle to fully cure. The pre-impregnated products consist of a combination of a matrix and fiber reinforcement, available in unidirectional form and fabric form. All 5 of the major families of matrix resin can be used to impregnate various fiber forms. The resin is then no longer in a low viscosity stage, but has been advanced to a B stage level of cure for better handling characteristics. Products available in prepreg form: unidirectional tape, woven fabrics, continuous strand rovings, chopped mat. Prepregs are cured with an elevated temperature, usually around 250 to 350 degrees F. Dry fiber material. Dry fiber materials such as carbon, glass, and Kevlar are used for many aircraft repairs procedures. The dry fabric is impregnated with a resin just before the repair work starts. This process is called wet layup, used extensively in the home-built market. The disadvantage is that the process can be messy and the reinforcement properties are less than prepreg material properties. Thixotropic agents. Thixotropic agents are gel-like at rest but become fluid when agitated. These materials have high static shear strength and low dynamic shear strength at the same time to lose viscosity under stress. Paste. Adhesives. Used as an alternative to film adhesive, used to secondary bond repair patches, T-damaged parts, and also used in places where film adhesive is difficult to apply, usually made from epoxy. Disadvantage: bond line thickness is hard to control. Film adhesives. Structural adhesives for aerospace applications are generally supplied as thin films supported in a release paper and stored under refrigerated conditions, 18C or 0F, available using high-temperature aromatic amine or catalytic curing agents. Foaming adhesive, usually 0.025-inch to 10-inch thick sheets of Stage B epoxy, used to splice pieces of honeycomb together in a sandwich construction, and to bond repair plugs to the existing core during a prepreg repair. Description of sandwich structures consists in its simplest form of 2 relatively thin parallel face sheets bonded to and separated by a relatively thick, lightweight core. The core supports the face sheets against buckling and resists out-of-plane shear loads. Properties: high bending stiffness at minimal weight in comparison to aluminum and composite laminate construction. Most honeycomb are anisotropic, that is, properties are directional, not necessary to use external stiffeners, such as stringers and frames. Facing material: most honeycomb structures used in aircraft construction have aluminum, fiberglass, Kevlar, or carbon fiber face sheets. Carbon fiber face sheets cannot be used with aluminum honeycomb core material because of galvanic corrosion. Thinner reinforcements from 3 to 4 plies do not have good impact resistance. Core material. The most common core material used for aircraft is honeycomb, and is usually made of an aramid material named Nomex. Some other types of core materials are kraft paper, thermoplastics, aluminum steel, specialty metals, titanium, aramid paper. Fiberglass, carbon ceramics, honeycomb core cells for aerospace applications are usually hexagonal. The direction parallel to the sheets is called ribbon direction, the direction that it can be pulled apart the easiest. Higher density core is stronger and stiffer than lower density core. Foam cores, used on home-built aircraft to give strength and shape to wingtips, flight controls, fuselage sections, wings, and wing ribs. Not commonly used on commercial aircraft. Foam cores are typically heavier and not as strong as honeycomb cores. Some types of foam cores are polystyrene phenolic, polyurethane, polypropylene, polyvinyl chloride. Balsa wood, natural wood product. The density is less than 1/2 of the density of conventional wood products, not to be used for structural application. Manufacturing and in-service damage. Some manufacturing defects include delamination resin-starved areas, resin-rich areas, blisters, air bubbles, wrinkles, voids. Thermal decomposition of part is resin-rich. If too much resin is used for non-structural applications, this is not necessarily bad, but it adds weight. A proper ratio for composites is 60-40, fiber to resin ratio. In service defects, fiber breakage can be critical because structures are typically designed to be fiber dominant, i.e., fibers carry most of the load. Fibers failures are typically limited to a zone near the point of impact and is constrained by the impact object's size and energy. Matrix imperfections usually occur on the matrix fiber interface or in the matrix, parallel to the fibers. These imperfections can reduce some of the material properties but are seldom critical to the structure, unless the matrix degradation is widespread. Delaminations and debonds. Delamination form on the interface between the layers in the laminate. Can also form from production no adhesion along the bonding line between two elements. These delaminations can grow when subjected to repeated loading and can cause catastrophic failure. Some of the critical factors of delaminations depend on dimensions under 2.5 equals resin injection, over 2.5 equals scarf, of delamination, location, loads, corrosion. Many fiberglass and Kevlar R parts have a fine aluminum mesh for lightning protection. This aluminum mesh often corrodes around the bolt or screw holes. Composite structures need to be protected by a top coating to prevent the effects of UV light